Hey everyone, I just wanted to thank you for joining. We have a great turnout and some fantastic information to discuss today. We'll jump into the first portion of the presentation in just a minute, but I wanted to do a quick introduction of Ingenuity Systems, how we're involved in this, and then provide some information about our panelists who'll be speaking about how they are implementing IoT platforms into the building management industry today. Ingenuity Systems has been creating BAS, BMS, and OEM solutions for 25 years. We have been designing Adesto parts into solutions for 20 of those years. Ingenuity has been at the forefront of the IoT movement, designing systems and implementing over 4,000 locations in US and Canada for the cloud-based IoT control application that we developed in 2006. I've got Steve from Building IQ, who leads the product and marketing at Building IQ to bring a suite of cloud-based energy intelligence services to commercial, healthcare, education, and other building markets. Steve ran marketing for Echelon in his earlier years before they were Adesto, and he's partially responsible for shaping the smart building market that is existing today. Steve holds an MBA from the Carroll School of Management at Boston College. Then we got Tim from Allied Intellisys. He's the Chief Operating Officer of the IoT engineering platform Evangelant Systems, a division of Allied Intellisys. Tim's experience includes over 20 years of engineering, design, development, and field deployment of the software and hardware solutions supporting digital transformation in public transportation agencies, city and local government and private industries. And last but certainly not least, we have Sammy, who has been in the control industry for 13 years and has engineered and installed systems for some of the largest companies in the LA area, and he'll touch a bunch more on that later. He has a BS in computer science from Cal Poly Pomona. At this point, we're going to pass the presentations over to Steve, and he'll begin. There is a chat feature where you can ask your questions. We're going to try and save questions as much as possible for the end, but if it's really urgent, there's a hand raise feature that you can use, and I will try and get to your question as soon as possible, okay? I have made Steve the presenter, and go ahead and take it away, Steve.
Thank you. Can you guys see my screen properly? Thanks for the introduction. Perfect. I'm Steve Million with Building IQ. And just to go through real quickly, introduce our company. We're in the building optimization space, so that's energy, comfort, operational processes, etc. About 120 odd, 130 odd million square feet under service. We've been around since 2009, and we're one of the rare kind of energy optimization companies that is publicly traded. And we did that as a funding round back a few years ago, like 2014 or so. I'd like to talk to you today really about how we are working to transform the building management system into a digital twin and basically an IoT system. This group of words is actually just a cut and paste out of Wikipedia. But what's interesting to us is the selection in red, which is all about creating a digital replica using artificial intelligence and machine learning. Something that is kind of learns from itself, from people, from its experience, leverages the environmental factors and changes the environment and integrates historical data. And that's basically the way we approach transforming a BMS into an IoT system. So from my perspective, the BMS was the very first IoT system. It just tended to be locked behind, kind of an old school PC, if you will. And then along came routers that integrated it onto the web, and then all of a sudden you had, in some buildings, the ability to treat assets within the BMS as IP hosts. So that was the beginning of the transformation. But what happened is we began to apply software services and software onto BMSs. We were still kind of entrenched in the rules-based world. Kind of like this example is, if this then that, which is something I use in my house to coordinate the, Google Assistant and Alexa and Lutron devices and Nest devices and all that stuff. It's a way to bring it all together because they're non-interoperable. But it's still rules-based. I have to know what I want. I have to know the outcome I'm after. The more sophisticated and the way to do it and the way the industry is moving is towards using AI and machine learning, reinforcement learning. So these techniques, we primarily use machine learning. We use reinforcement learning, optimization, and optimization models for specific buildings. Transfer learning is taking learning from one building and applying it to others. And extreme learning is a much newer methodology that we're applying to buildings, wherein we look at the entire data set and modulate the parameters on that entire data set instead of trying to use discrete analytics and just kind of narrow down the focus of those parameters. So this is the way we're moving. And the benefit of it all is to take that building system and begin to do things like baselines that are not invasive or don't require a lot of people, so you can do prediction, doing fault diagnostics and analysis and root cause analysis that doesn't involve a whole bunch of rules, but instead involves just a bunch of algorithms. Smarter commissioning and retro-commissioning, dynamic demand response, where it's actually tuned to the environment, and ultimately closed-loop optimization, which is another way of saying the building doesn't drift. So you're always running at the lowest possible energy consumption, if you will. So it runs the gamut when you apply services to a building that's been unlocked and treated as really kind of a sophisticated IoT system that has a lot of edge computing capabilities, but it can also be integrated with the cloud. Won't go through a lot of our services, but we are part of the building process from soup to nuts. But I think what I want to touch on before we get into the specifics of how we treat the building as an IoT asset is when you start looking at buildings as data systems and all the components of a building as a data system and begin to tie those pieces of data together, catalog that data, make it searchable, be able to run analytics against that data, you begin to build a really fundamental industry knowledge or domain expertise around the building. So where before you may have had people on site for 30 or 40 years that have that domain expertise and then leave, you can de-risk that whole situation and begin to encapsulate that into the database systems that are the cloud systems that govern the building. And it is not a replacement, it's an augmentation of the existing staff. So operational asset, energy data is integrated, the system level interactions are cataloged and captured. You can use it for prediction. All of the discussions and triage around finding root cause analysis are available. Anomalies and contextual data, you can decontextualize anomaly or add context to an anomaly, so on and so forth. So it becomes a very deep knowledge system over time as you begin to treat these buildings as digital twins with IoT systems and catalog and capture everything that occurs in those buildings. So let's talk very specifically about how it can be used for for facility optimization, from analytics to predictive control. And we'll start the journey in this case with the notion of facility guys who need to understand what's going wrong in their system. The problem is with a building system and alarming, there's just so many, and you have to know what you're looking for. So it becomes just a lot of background noise. We've talked to clients who have 300 to 500 alerts a day. Just like they spend all their time just kind of churning through these things, trying to figure out what to do, and it's just overwhelming. And so the trick is to go away from this data deluge and get to actionable information. This is a screen capture of one of the buildings we have, and you can see we're tracing a lot of points. And this is only some of the points that we track, but you can see it's already overwhelming unless you're a data guy who spends all his time looking at charts like this, which are few and far between. And as you begin to remove some of the data, you begin to see anomalies, of course. You can capture those anomalies and annotate them and begin to take them into a triage mode where you have teams looking at it. So in this case, it's a chiller issue. So we're moving away from pure data to kind of analytics to trying to arrive at root cause. And as you do that, it still is a somewhat overwhelming problem, and I'll show you in the next slide in particular how that works out. But you can see here alone, the dots kind of represent different assets or data within assets. The size of the dot indicates the number of things that it either impacts or is impacted by. The width of the lines indicate the strength of that impact, and the arrow has defined the direction. So what we're doing in here is we're using the data from these devices not as part of the BMS, but as discrete IoT data points. So an IoT point may have anywhere from 1 to dozens of data points. So it could be something simple, super simple, like a temperature sensor, or you could treat an IoT point like a VAV box in an HVAC system where it may have 40 different discrete pieces of data. And so we're building from the ground up, starting with the data coming from an IoT device, building it up into an asset, building it up to the zone, building it up to the system. But it has to start at the data level. So you can see here, we're pulling in a lot of data and trying to figure out head from tail when you look at this data. And what's interesting is you can, of course, apply filters to the data. And as you apply filters to the data, you can begin to key in. So this case, we're talking about that zone that's highlighted in green in just a moment. And I wish I could stop this, but I can't. But it's showing which pieces of data, and therefore which assets are tied to that anomaly, that behavior. So instead of being confined, like in the physical world with how things are connected by wires, we're really simply focused on the IoT world, which is how things are connected by data and by action. So the correlation of data movement between devices is what's important, not necessarily the physical interaction of those devices, physical connectivity of those devices. And when you do that, you break down all those kind of barriers or preconceptions about how a system should work, and you're looking at really how a system actually works. Is it the window that's open on the west side that's influencing the temperature on the east side, as opposed to the T-stat itself, right? So those are the kinds of things a very experienced facility manager might know, but it's also very difficult to pick up in the digital world because they're very discrete systems. Of course, there's no sensor on that window. So these are the kinds of things we're beginning to capture as we do root cause and deep analysis using AI tools and treating the BMS as a collection of IoT devices and the data contained therein. So that's one way to look at activity, anomaly detection, and root cause analysis. The other way you do it is you treat that as a foundation for learning, and you begin to do stuff with that information. And one of the things you can do is control. And in this case, we're talking about predictive control, where you created a model of the thermal capacity of the building, and then you're using the data analytics to modulate how that model behaves from day to day to day. So the model is in a learning model. It rebuilds itself every night, but it's rebuilding itself off of data that it encounters. So we're talking about the environment, we're talking about the operations history, we're talking about the weather history, we're talking about the operational tenant occupancy history, and then you're looking forward in time. What's happening over the next 24 hours on an hour-by-hour basis, or as long as we can get that data. And the longer we can get an hourly forecast, the more further out we can predict. And then what the system does, again, treating it really more as a collection of IoT devices, is you can begin to tune it. You can tune it for cost, and the energy cost. You can tune it for demand. You can tune it for comfort. And one day when we all figure out kind of collectively how to tune for productivity, we'll do that too. But the interesting thing here is, again, treating it less as a system, like a BMS, a monolithic BMS, and treating it more as a series of IoT devices, pushing out that kind of control paradigm into the edge, and the edge in this case could be either the individual boxes, or it could be at the zone level. They could actually, sure, it could be down at the device level too in the rooms, but you can do all of that. And you can do it in a predictive way that is beyond the capacity of most humans to do. In other words, if you have a large building you could have a team running around and modulating temperature or looking at the BMS screens and going in one by one and doing all that stuff. Or you can do something where the cloud is figuring out what has to happen hour by hour by hour based on the forecast, and then modulating the different parameters in the system, in this case, zone target temperature, to achieve an efficiency. And that's all done automatically in the cloud. It's pushed into the building does this thing, and the building owner still and the building team still have control over what's happening on site. So it's never taken fully away. It's always left to the facility manager to apply their own expertise, designed to augment their capabilities so they have a nice smooth curve for energy efficiency throughout the day, and they can deal with anomalies on site. And that's the way predictive control works, hand in hand with facility teams, leveraging the full capabilities of VMS, and yet augmenting it quite significantly. And so one of the beauties of that is, as you move through the course of a year, you can transition from efficiency to demand. So you can go, let's say, from a cost-based efficiency, where you're trying to minimize your costs for electricity for the whole building, to some kind of time-constrained demand event instituted by the utility that you're participating in. And it just happens seamlessly. And the beauty of it is that when you're in the DR mode, it's actually leveraging what is learned from the efficiency mode. And it's all done through software in the cloud. So if we net it all out, if we look at it from a kind of an Industry 4.0 perspective, we've got labor, service, resources, and processes, and asset utilization as our kind of 4 buckets. As we look at the overall benefits for analytics control. And if you apply cloud-based services on top of IoT systems and buildings, this is sort of the range of benefits that we see. You reduce maintenance, productivity increases, which again are pretty hard to measure, reduced equipment downtime, and increased productivity of the knowledge work. So we see that in our client base. It's beginning to characterize maintenance and downtime using something called remaining useful life, and beginning to bring in more and more kind of tangential assets or tangential knowledge into the way we leverage the IoT systems and buildings. So tangential knowledge being things like historical work ticket information that's actually syntax off of the comments in the work in the support systems to understand how things are working, using influence engines to understand what has the most impact on energy, and then using a correlation engine to understand if that thing has the most impact, what is it impacting systematically, and then knocking down the barriers of what the system is to take away from the IoT to human processes. So those are all kind of things in processing things for the future as we think about how we can leverage a sophisticated IoT system like a commercial building. And thank you for your time. That's it.
Thanks a lot, Steve. We're going to be switching over to Tim Hopkins from Allied Telesis, and he's going to just knock it out of the park for us. Go ahead, Tim.
Hey, well, thank you very much, Mike. I appreciate that. Steve, it's always good to kind of hear what you guys over at Building IQ are doing. You're doing a lot of great stuff up there in the cloud with all this data, and listening to you guys is a good educational experience for us over here all the time. So thank you for having Allied Telesis participate. And before I keep going, I'll make sure that first 2-minute monologue, everybody could hear that. I make sure everybody's okay here. You can see my screen as well?
Yep.
I will take that. Okay, great. Perfect. Okay. So what I wanted to cover today was just a couple different, the headlines, kind of who is Envigilant Systems, some of the challenges we see in brownfield deployments, and a couple case studies of projects that we're either working on or we've kind of finished up deploying. So with that being said, who is Envigilant Systems? And we're actually a part of business unit, part of Allied Telesis. So Allied Telesis has been around for 30 plus years, Our headquarters are in Japan, in Tokyo, Japan, and but we have a worldwide presence with R&D facilities spread throughout the globe. A couple main offices here in North America in San Jose, Silicon Valley, in North Carolina, and some software offices down in Christchurch, New Zealand. Our span of products range everything from small media converters, NICs, and transceivers all the way up to larger products such as firewalls, access points, switches, routers, stackable chassis, these types of things. And some people might wonder kind of how does that fit into IoT, and where is Vigilance as a part of that? So we're actually a group that kind of for about the last 4 or 5 years now, we've been leveraging our history in networking to provide more engineering capabilities to our customers. So instead of selling the traditional software and networking products into the networking space, IT space, and Vigilance Systems focuses more on the solution and services directly to our customers. We've addressed problems in the transportation space, manufacturing, smart building application type areas, and that involves everything from leveraging connecting sensors and devices through the networks up to hosting cloud-based solutions for our customers to analyze and look at the data that they have. And this all essentially is backed by our experience connecting these devices at the physical layers. So one reason why we're doing this as part of the Vigilance Systems group is as we worked with our customers over the last 30 years, and I've been at Allied Telesis now for more than 16 years, close to 14 years. Our customers said, we've got your equipment helping to connect all these different points and devices throughout our network. We're starting to add more and more sensors, and they turn to us to help us continue to connect these devices, try to figure out what kind of data and insights they can get from them, and how our knowledge, Allied Telesys' knowledge of their network and their underlying systems, we can leverage that to help them better understand what's on their networks, what's connected at the edge, what kind of sensors they can additionally deploy and layer on in order to get more business insights. So this, leads into the IoT world. Steve spoke a lot about the data and the insights you can derive from collecting all of this information. So one area we've done is we've been working with Echelon's now Desto, and using their smart server devices and even some of their legacy devices, which I'll speak more about in one of the case studies, using this type of physical connectivity to connect these disparate data points and then layer on different applications to help our customers derive these insights. So some of the challenges in these brownfield deployments, as they're called, so we've been working with these customers, in many cases 10, 20 years, and these networks is not a brand new building in many cases, or a brand new facility or a manufacturing floor. A lot of these facilities, they've got sensors that are already deployed, networks that are out there, and we need to interact with these things, and they can be disparate systems. A multitude of protocols might be out there. Some might be connected over, Ethernet. Some be connected over, BACnet, Modbus. These are different, protocols that are out there. There might be no documentation on these systems. The data is siloed. Each vendor has come in and put in kind of their system, whether it's controlling door access control, smoke alarm systems, these type of temperature control. These are all standalone systems. So utilizing solutions that customers can kind of pull these different disparate silos of data together so that the information is not broken. You have to log into one machine, log into another machine to get all these systems. We're trying to get all that together for these customers nowadays. So this provides the opportunity to get more real-time access to information. You can start doing predictive maintenance and analytics that Steve was talking about, supporting the whole digital transformation from some of these agencies. A lot of them are challenged that we'll see in the public sector space, for example, in transportation. When these large agencies deploy or upgrade systems, they can be financially challenged, let's say. And so they don't just get to go overhaul a complete system. They might be, 3 different types of train cars might be running on a particular network, different types of buses in a bus fleet, different platforms for buses and trains could have been upgraded with different systems over time as funding became available. So there's a lot of disparate systems that are out there. So the opportunity to connect all this stuff together and to help these agencies go through this transformative process where they can start to gain real insights can lead to the value, unlocking the real value in this data. So a couple case studies that we've looked at, and I kind of throw these little pictures up here to show how we've gone from old legacy buildings or trains or even factories that are built sometimes 30, 40, 50 years ago, how we can go from these old legacy systems and kind of tap into what some of the new opportunities are to go into there and make these housing deployments or manufacturing or buildings or even transportation systems more state-of-the-art without having to go replace the whole system, tear down buildings. What kind of opportunities exist there to really embrace this digital transformation? So one of the first ones we'll look at is Army barrack installations. So as many of you know, the Army has numerous installations throughout the world. These could be permanent installations, these could be temporary ones in an effort to support advanced forward deployments. And so what the Army was looking to do is, this is a current project that they're trying to gather more information on and craft a solution to how do they create these barracks where they can house thousands and thousands of people in a dense environment. How can they create a more installation of the future is what they called it. So they want to integrate, whether it be commercial off-the-shelf systems, legacy systems, and add in the capabilities to integrate real-time information into simple things such as the fire alarms, carbon dioxide monitors, thermostats. A lot of those things that Steve was talking about is how we can get these systems together. So they're going to want these cloud deployments so they can understand what's going on in these areas, but that piping, the actual infrastructure in there is kind of where Allied Telesystems and Vigilance Systems has really built up a working knowledge of how to integrate these different systems together, because having a cloud deployment or having the applications to look at the data, you still need to get access to the data that's sitting at these systems and pull it all together. So many times, this is where the Army is having the challenge of, how do we connect these different systems? What kind of interfaces? This is where, working with an Adesto solution, their smart server, these types of products that can, speak multiple protocols. They can, output in standard formats, standard APIs, give us the ability to go in there and really connect these systems together and enable this transformation to the installation of the future. And this is, like I mentioned, this isn't just an Army looking at doing this. This is something that they're really putting money, time, and resources into. So these are real-time opportunities for companies and agencies to go out and kind of help support this process. Building and manufacturing automation. I won't talk too much about the building side of it. What Steve is doing and the next panelist will be talking about. They've got a ton of experience in some of the building side of it. But once again, these systems in these buildings, these legacy buildings, many times they're old systems that have been in place for several decades. When people go in and install some of these systems, they don't expect it. It's not like a computer where every couple of years, you upgrade your computer, you're on the next operating system, or Intel comes out with the latest chip, so let's throw away this computer and get a new one. When these buildings are constructed, they put in systems that they plan to have in place for several years, if not decades. And so some of this stuff they're old systems and it still works. So how do we leverage connecting to that and bringing it all together so that a company like a Building IQ can go in there and get that data? So this is kind of one of the areas that we've really been focused on, is working with these partners and these customers that we've deployed this networking gear and helping them to pull all this information together. In the factory space, same challenge there. Many of these, we have a large automotive manufacturing parts customer where they'll build a machine that, can be, 50 feet wide, 30 feet long, and 20 feet high, and all it does is make one particular widget for a part of a car, and it does it 24 hours a day, 7 days a week. And they've got PLCs connected to that, robots, and this machine costs them millions of dollars to build. And they want to start layering in more sensors and get more insight into the machine so they can increase the productivity and drive the performance there. So they can't just go out and build a new machine. It takes years sometimes to get these machines designed, built, fine-tuned, and so they want to be able to go in and add in sensors that will connect to optical sensors or the robots that they've got running these things. And so connecting legacy systems here is critical because there is no opportunity to just rip and replace. That's not an option. So as we build these systems for the manufacturing space, there's unique requirements. It's got to be resilient to high temperature or dust. This environment isn't, your nice, clean data center where the temperature is controlled and the air is clean and filtered. These things have to be working on the factory floor where there could be moisture present. And it's a little bit of a challenge many times in these places to get this stuff all, working in harmony and rugged enough. So just kind of it's one of those challenges where it might seem easy at one point to say, hey, we can just go hook up some machines and start getting this data and derive these big insights and just say, hey, if you tweak this one knob here, your machine's gonna, start producing, 10% more efficiently. It sounds great, but there's really a lot of pain that had been part of connecting these old legacy systems at times. Which kind of leads into the last example here, and this is one project that we just completed working with a large transportation agency here in the region. And these pictures over here I show on the right are some old legacy Echelon devices that you can see the logo on there. So these are actually devices that are deployed onto a light rail system, and they've been functioning now for 10 plus years, and they monitor everything in the train with regards to tractive power, HVAC units, braking, door sensors, all these different subsystems are in the train. And these devices in each particular train, as you see in the picture there's 3 of those devices in the top picture and 2 on the bottom. So that group of 5 devices, there's a group on each end of the train. There's an A and a B end of the train. So, and each end of the train has all these, there's a train network and a car network. So all these devices and subsystems of the train are being actively monitored in real time through these Echelon devices, through the LAN network that's been established and put in place. So all this information that these devices are monitored is actually displayed on these screens that are in the train. So as you can see in these pictures here, one's a graphic from a manual, and the other picture there on the bottom right is actually a display in the train showing what's being monitored. So you've got the propulsion, the auxiliary power, and you can see on this particular train, the train number is 929. You can see there was a couple, the red rectangles are the things that were in fault, and the green ones are the current status. So all this information is being actively monitored. One of the challenges here is this information sits on the train. It doesn't real time get collected, pushed up to the cloud, or pushed up even to operations. So one of the projects we had to do here was to deploy a new security system. So let me go into kind of what the project was as far as tapping into the legacy devices on the system and what we had to do. So the project was we had to deploy a new security system on the train, which involved cameras and offloading real-time information from that system. But in order to meet some of the requirements, we needed to understand what the configurations of the trains were, which cars were connected to each other, the active end, the trailing end of the train, where the cars were in the particular consist. So all that information needed to be actively pulled real time so that the camera displays, the driver camera displays, we would know which cameras to feed to which end of the train. And the only way to get all this information was actually to tap into the legacy LAN network because all that data was there. So this was a perfect example of attaching to a legacy network and using devices that were still active and reliable, yet one of the big challenges was all the what they call the data dictionary on what all these the devices are talking to wasn't available anymore, because this was a 10-year plus network. So we had to sit down and work with the Adesto engineers, dig into some of the network on the train there, and kind of manually decipher some of the codes, but still the information was all there. It was clean. The legacy system was good, and wasn't something where you could just rip everything out and put in a new system. The cost there would have been prohibitive. But through a number of iterations, we were able to get the information that we needed, and we were able to feed all of that into the security system so that we could display the proper information security-wise, so we know which trains are connected to which, and we could dynamically send all the video information through the network, so we knew when the doors were open and closed, the orientations of the cars. In the case of an incident, they could pull all the video data. That information helps to drive. Here's a small picture of what we've got going as far as a dashboard. Something as simple as seeing in a red circle, we know which two cars are connected together. We know the orientations of the car. We know where it is in the network. We're able to now get all this information that was on the lawn network as far as propulsion, tractive effort, braking. All these faults and diagnostic points are now able to be collected, aggregated real time, put into a monitoring system, and then aggregated to provide more predictive and reliable maintenance schedules. The train in the blue box there, just as a single train, there's no other car connected to it. These cars can be 1, 2, 3 car consist, as they're referred to as. So getting this kind of real-time information from a legacy system provided a tremendous amount of value and insight, and it was almost a secondary benefit from an initial project that was being carried out. And as an example of one of the values that this data was able to provide that wasn't available before was, we're reading, as I mentioned before, the doors open and closing, so that we would know, which kind of camera displays to show to the driver, so they know when passengers are getting on and off. We were able to read all the sensor states from all the different doors, and so this is just a quick little screen without going into all the details. It shows us which relays are opening and closing, and if any of them are getting stuck or not closing properly, trying to figure out what's going on there. Is the door in a position where it's starting to become faulty? Does the door need maintenance? Did something block the door? And so by aggregating this information to understand if the door got stuck, we're able to then give better insights into what is the functional state and the capability for VTA to provide that type of maintenance. So aggregating the data, here's a slide, a graphic that shows all the different door states of the relays. And one of the big ones to take from this as far as insights is the green one that says bounce stuck. And what we're able to tell from this is that many times the passengers are getting on and off the train, and the train's about ready to leave and the doors are closing. Somebody will stick their arm in the train door to hold the door, which is, it's not safe for the passengers, and it definitely can cause issues with the doors, because these doors are not meant to be, held open. So people will hold the doors open, they'll jam them open while people can let other passengers on or off. And so this can cause issues with the doors later on. So getting this type of information that in the past, none of it was collected, and it definitely wasn't aggregated across multiple trains or real time. This kind of information from a legacy network really gives customers the ability to then make informed decisions to understand how can they address these types of problems in the future. How can they then go fix doors that are starting to show symptoms of having an issue, whether it be from just wearing out or from people that are jamming them open. Because one of the things that they don't want to have to do is have a train that's out during the middle of the day and all of a sudden the doors stop operating, and they've got to have all the passengers get off that train and bring that train back into the yard and send a whole new train out. It's much easier to take care of the doors in the yard in case there's any type of maintenance needs, rather than having to go deal with the issue out in the field. So deriving these types of insights from systems that are already deployed, whether it be in a building or in a factory or in transportation sector, is really an area that that we work with our partners, we work with our customers to figure out what can we do with the existing deployments and systems that are out there. So with that being said, I turn it back over to Mike, and if you have any questions, please let me know.
Thanks, Tim. I've shot it over to Sammy, and he'll be sharing his screen right now. Go ahead, Sammy. Thank you.
Hey, thanks, Mike. And Tim, I love that that example of the train car system. You know, as an integrator, that's always something, you know, pretty interesting to see. We work in the building market, so we don't come across stuff like that. It's pretty fascinating from an engineering and technology perspective. So thank you all for joining us this morning. My name is Sammy Arbid. I'm with Western Allied, Senior Controls Engineer, and today we're going to be talking about multi-site secure cloud management for building automation. Mike already introduced me a little bit, so I want to talk about Western Allied. For those who are not familiar with us, we are a large design build mechanical contractor in Southern California, in the LA area. And we've been here for over 55 years. We started in the early 60s. We have a proven track record with multi-tenant office buildings. We do some hotel, retail, biotech, and pharmaceutical manufacturing facilities. But mainly, we work with a lot of entertainment facilities. Tend to have a lot of studios in the Los Angeles area, so they keep us busy. We started our controls division in the late 90s, and shortly after we jumped onto LawnWorks. And so we've had a long history with designing, building, installing, and supporting lawn controls systems. In the more recent years, we've actually started installing lawn and backnet multi-protocol systems. Those have been really interesting, and we have a lot of customers who have been asking more about that. And we were the first mechanical contractor in Southern California to be certified as a LawnWorks system integrator. So long time LawnWorks integrator. Some of our more notable customers, you guys might recognize some of these brands. Allergan, they're a pharmaceutical manufacturer. Eisenhower Medical Center, they're a very large hospital in Rancho Mirage, Southern California. And they have some 30+ buildings that we have controls all over. And we help them across their whole campus. I won't go into each and every one of these, but you can see down below, you know, we do a lot of studio work, Universal Studios theme park as well. You know, Western Allied is a little bit different than a typical controls contractor. So not only do we design and install control systems, but we actually maintain them. And we actually operate them on behalf of the building owner a lot of the times. So that means we're often functioning as the tech support for their on-site building engineers. So you can imagine that remote access is extremely important for us. It drastically reduces our response time for support, and often means that we can actively monitor new systems to work out kinks before the customer calls for complaints. So how do we actually manage to remotely access all these systems? Before we talk about that, we need to understand a little bit about what a traditional building automation system looks like. And I've got a little diagram here with the 4 layers, where the lowest layer, we have sensors, relays, and actuators, which all interconnect to a set of controllers. The controllers read the sensors and output control signals to the relays and actuators, which are controlling equipment for us. The controllers then interconnect on a distributed network, so they can share information between each other, as well as with a central server. And at the top of all this is that central server. So it's typically a web server, and so that web server does a couple things for us. It's a operator or user interface for the system, and more importantly, it connects the control network to the building's data network, which gives us the ability to send alarm notifications and remote access. So what does remote access look like? Well, there's actually a few different ways to do it. The first approach is to take a traditional control network and just connect it to the public internet using a firewall. So this allows the public user, a user on the public internet, to access the control network. And typically when this happens, the integrator doing the work, they may not even know what a firewall is sometimes, and they may not install firewalls. So they just literally plug the system directly to an ISP modem and expose the system to the internet with no security whatsoever. And anybody who's had to deal with the other side of this has learned that these automation devices are really not designed to be publicly accessible for remote access. They can't really take the hit that that internet traffic can sometimes burden a system with, and more importantly, you can leave your control system vulnerable to hacking and DDoSing attacks. So there's really an expertise needed to install these systems and configure these firewalls. You have to be able to understand IP addressing, what a NAT network is. You have to be able to map public IP addresses to private IP addresses, set up port forwarding, and understand which services are available on the control network and should be exposed on the public internet. And most importantly, and it's almost never done, is restrict the source IP connection or apply geo IP filtering. So that's really the ability to say, okay, we're going to allow connections from the public internet, but only from this range of IP addresses. And that range of IP addresses could be regional, or it could be, let's say, the known IP address range for a headquarters building of some sort. And so that's rarely done, but it really should be. The second approach is to connect over a VPN, a virtual private network. So VPNs allow you to remotely connect into a corporate network as if you were physically in the building and plugged into a switch. VPNs are typically available with large organizations that have IT staff. And usually integrators are not able to provide VPN solutions. They're pretty cost prohibitive, they're expensive, they require a much higher level of network engineering and expertise, and there's always ongoing support with them as well. So some of the impacts of having to use a VPN are that it restricts the control system's connectivity to the building network, and it may even limit the outbound communication to the internet. So you may have a control network that can't do alarming, for example. It can't reach out to the internet. Well, there are many VPN vendors as well, and they have several different configurations and methods of authenticating. So definitely the complexity goes through the roof when you're having to manage multiple systems that each have a variety of VPN solutions. The last option is to install an on-site PC of some sort and then connect to that PC using a third-party service, something like TeamViewer or GoToMyPC. But that really means you have to, A, provide a PC. It has to be something that if there's an IT group involved that they'll bless. You need to maintain the PC. You need to be able to give it the security updates it requires, and as well as provide all your engineering and programming software on it. And I don't know of a single integrator that actually installs an on-site PC and does the maintenance on it. They'll usually install it. They'll do all their commissioning, make sure the system's working, and then they walk away from it. They never hear back from the building unless there's a problem, but then it's usually too late. So many corporate IT groups actually block access to these third-party servers, and they kind of view them as a backdoor. So not always an option. So moving into the future, we're now able to actually connect these systems to cloud-based systems, which means as far as architecture goes, we have a couple of changes. The first is that we can now separate management from the physical building network. And so we basically can divide building automation into two networks. There is the lower network, which we refer to as a field bus or control network. It's going to reside in the building, and that's where all the controller-to-controller messaging happens. And then there's the upper layer, which we're going to call the central management network. That can reside in the building or it can reside out. And it's really responsible to be the user interface and to handle building schedules, data logging, alarming, things of that nature. The second change is that we really no longer have remote users reaching into the building network anymore. So instead, an edge server can be installed on the cloud network, and it's reaching out to the cloud server, as well as the remote users who connect to the cloud server. So this architecture kind of allows us to have multiple buildings all connect back to a central management server. You can have any number of systems connected, and that central management server can actually contact other cloud services as well, so you can have much deeper integration, which is something Building IQ, for example, is involved in. More importantly, this actually kind of simplifies network architecture within the building. You no longer need to provide firewalls. You don't need any additional network infrastructure. You can take advantage of automatic network addressing. And the edge server doesn't really need to know a whole lot about the building network. You kind of more or less kind of plug and play. As long as it gets an internet connection or some means of connecting back to this central management server, you're kind of done. So Adesto's latest smart server enables this architecture. The smart server IoT can securely connect existing and new systems to your central management software. They're calling CMS. Smart server IoT can run the CMS on its own hardware, if it's a small system. So you can model traditional building automation architecture, or if you need something cloud-based or maybe for larger systems, the CMS can be moved to an on-premises server, or it can be moved onto to a cloud VM instance. And of course, this all gets installed on top of traditional LAN and BACnet Modbus systems. So we can take those legacy systems, instead of abandoning them, bring them forward to the future. And that's all I have. Thank you.
Thanks, Sammy. I'm going to switch back over to my screen here real quick and go through a couple of questions. First question was for Steve. Steve, how much data is typically required before machine learning can effectively control systems? Is it days, weeks, months, years? What kind of time frame are we looking at?
The way we do it is a light touch. So we try to get anywhere from 6 to 18 months of historical whole building meter data. So 15-minute interval data if possible. An hour interval data is just fine. And then the tenant history, the BMS history if possible, and the weather history. That allows us to build a thermal model at a zone level. So that's all we need, which is really not a lot. And then after that, it's a pretty light touch, really focusing on 3 or 4 parameters on the control side. It's not an invasive touch where you're working with every single IoT device. You're really kind of leveraging the edge computing capabilities, if you will, of the BMS and saying the zone target is this, and then do your thing, BMS. So that's in an ideal world, it's very, very light touch, so not a lot. If you're talking about analytics, then you are talking about 16,000 data points pulled at anywhere from 1 minute to 1 hour intervals. Okay. And then it becomes a load on the BMS, so you have to be a little careful about how you pull data and in what interval. Okay. I hope that answered the question. If not, you guys can follow up again. I got another question here about how are you guys looking to take advantage of CBRS for private cellular use case for safety connecting devices to the cloud? Sammy mentioned the issues with VPNs.
And I'm not familiar specifically with CBRS acronym, but maybe you guys are. Anybody that wants to field that one, we've got a couple of minutes left.
Yeah, I'm not familiar with CBRS either, Mike.
Okay.
Yeah.
I might take a stab at, maybe it's cellular band routing services. I could be way off. I know that in some of the locations that we have installed, there is credit card processing because it's a transactional type environment, and they don't want us on any of their networks, whether it's through a VPN, a firewall, or anything else. And we have provided cell router functionality to those customers so that it's completely separated and really quite secure. We've been doing that since 2007 or 2008, and it just keeps getting cheaper as data can be aggregated across sites and so on. So the potential for using that to keep sites more secure is definitely there, and the number of manufacturers that are manufacturing devices to allow you to do that quickly and easily is increasing every year. So I think that was from Brian. Brian, I hope that answered your question. If not, reach out to me and we can go. I got one more question that just came in. Is the question for Sammy about going into more detail about the preferred security system that you were talking about, and can you tell if it means that we have to still integrate with the IT department?
So if we're talking about the cloud-based approach where the edge server is connecting out to CMS, you will have to some degree, you will have to talk to their, the corporate IT department to some degree, but really all you're looking for is a data connection from them, right? So as long as they can provide a connection, they don't have to provide any IP addressing information. If they want to just, connect this device onto, via DHCP, that's fine for automatic addressing, that's fine. But really it just needs the ability to make an outbound connection. And as long as they're in the loop with that and they're comfortable with that, you're kind of done. So while there's still coordination that should happen, there isn't really a lot of configuration or time spent to make the connection happen. I hope that answers the question.
And then one last one, we got about 2 minutes left. Anybody can answer this. It's a question about how we can take, the smart server IoT and legacy system to the cloud, if maybe it's a BACnet system, a Modbus system, or even, one of the varieties of WAN. Whoever wants to try and field that one, we got about 90 seconds.
I can jump in really fast. I know we've actually been working with a couple of projects with cloud providers, and so I think one of the benefits of the smart server is the fact that it offers, the capability to put out, MQTT, offer REST APIs, so that a lot of these systems, whether it be, an IBM Watson type system or an Amazon or Google Cloud, the protocols that it uses or the APIs that are available to standardize into what's becoming, kind of the industry standards as far as that goes. It does all of that itself. So it offers, the capability of, in addition, a memory buffer. So if you happen to lose that connection to the cloud, because that's always a concern with some customers, is what if that data connection goes down? So there's capability for the device to store that memory in there, or those data points. But, being a device that operates with what are quickly becoming today's standard norms is one of the benefits, I think, that device offers.
Great, thanks, Tim. All right, guys, that's going to be our time for today. If anybody has questions that they think of moving forward, feel free to reach out to me. My email is mike@engenuity, ENGENUITY.com. This series has been recorded, will be uploaded to our YouTube, and you should be hearing back from us in the next week or two, giving you links to both video series that we've done. and allowing you to ask any additional questions at that point as well. I want to thank everybody again for attending. Have a wonderful weekend and a great 4th of July. And that's it for us. Thanks, guys.
Thank you.
Thank you.
Thank you, everybody.